Ever heard of Hawking? No, not Hawkins. Hawking. The late Stephen Hawking postulated a theory about black holes that sort of affects our very understanding of a substantial amount of the universe, and also provides an answer to some heavy questions in the field of general relativity, which is basically the study of how space works, and quantum physics, which basically is the study of how tiny things make up the entire universe. Now, if you're a little confused, welcome to the club. NASA recently launched the James Webb Space Telescope to help us understand certain things which will eventually let us know if Hawking was right or wrong. So just what exactly is Hawking's theory, and why is it important that we prove or disprove it? Well, pay close attention, and I'll tell you everything from our understanding of black holes and dark matter, and how this NASA telescope will help us peer through the fabric of time itself. What are black holes? Now, when you hear the words black holes, you immediately think of some big dark hole in space that sucks everything around it. If you think that, you're kind of right, but the thing is, black holes aren't exactly, well, black. It's more like they're invisible. In fact, we can't directly see black holes, but we sure see the effect of the space around it. Black holes are technically dense objects in the universe where the gravitational pull is so strong that it pulls in everything around it, including light. It does this so fast that it turns matter into a super hot plasma in the process. And we see this by observing the black hole's event horizon, which is the circumference around the black hole. Think of it as your vacuum cleaner, but instead of sucking all the dirt in your home, it sucks everything else and then just disappears. Scary, but hauntingly beautiful. Now, there are primarily three types of black holes. Primordial black holes, which are the smallest of black holes that range from the size of an atom to a mountain. They have relatively small size and mass and are believed to have formed at the beginning of the universe, all the way back to the Big Bang. This is actually the basis of Hawking's theory, but more on that in a sec. Next, we have stellar black holes, or collapsers, which are formed when a star collapses upon itself, hence the name collapsers. The collapse occurs by a process called a hypernova explosion, or simply a gamma ray burst. These stellar black holes are kind of the most common, and also the first kind of black holes we discovered, with the discovery dating back as far as 1964 in the area of the Milky Way called Cygnus X1. Lastly, there are supermassive black holes, which, as the name implies, are supermassive, at least in comparison to the aforementioned black holes. With the most recently discovered supermassive black hole being the J1144, which is 8 billion times the size of our Sun. It's so huge that amateur astronomers can see it. J1144 is said to be present at the center of the Milky Way, as most supermassive black holes are known to be present at the center of their galaxies. The very fact that black holes absorb massive planets and any matter around them, and then eventually evaporate, is something that has puzzled physicists for decades, because all that matter just goes in and disappears. Where is it all going? What really happened to all that absorbed matter? Some scientists have hypothesized that black holes are gateways to other universes and other realities, sort of like portals that just take stuff and vanish. But there's currently no way to verify that hypothesis, unless we actually go into the black hole itself. You're no Matthew McConaughey, so I wouldn't recommend it. Stephen Hawking, however, suggested that when black holes evaporate, it's not a portal vanishing. Instead, it's doing exactly what we see. It's actually irreversibly destroying itself. This breaks a fundamental law in quantum physics, which states that nothing is ever truly destroyed, that any process in physics can be mathematically reversed. But Hawking didn't stop there. He even went further to explain the nature of black holes in his theory of dark matter. Now, to understand what dark matter is, listen closely. Every visible thing in the observable universe, including all the suns, planets, comets, asteroids, and black holes, make up approximately 5% of the total mass in the universe. Yes, everything we've seen, are seeing, and will see is just 5% of what's out there. Let that blow your mind for a second. Einstein's theory of general relativity posits that massive objects in space exhibit a force, which we know as gravity, that warps space itself. Think of things in space, such as planets and suns, as massive magnets that pull things towards them because of their size. We also know that zero gravity is also in space, and that's actively trying to pull objects away, so that eternal tug-of-war keeps objects in place, hence the start of orbiting or falling around the circumference of whatever body of gravity that's pulling them in. This is how the moon rotates around the Earth, and the Earth around the sun. Let's take our solar system for example. The closer a planet is to the sun's center of gravity, the faster it rotates around it. On the other hand, the farther a planet is from the sun, the slower it rotates around it. That's easy to understand, right? And when we look at things in space, we find that these celestial bodies are in fact moving at higher speeds without any influence from gravity. We don't see anything moving them. It's not visible to us. So what's causing this movement? Scientists term this unexplained phenomenon as dark matter, because even though we can't see it, we know it's there, moving things and occupying space. Dark matter has an even greater counterpart that's not only moving planets and galaxies, but the universe itself, and we call that dark energy. Dark matter and dark energy account for roughly 95% of the mass of the universe, and we don't even see it because it rejects light. In fact, we have no idea what it's made of. This brings us to Hawking's theory of dark matter and black holes. Hawking theorized that dark matter is actually made out of primordial black holes. Remember the tiny black holes that I mentioned earlier? Seeing that black holes, like dark matter, reject light, we can't really see them, just their effect. It's tempting to think that this is the case. It would make a lot of sense, and not just that, this theory would also simultaneously unite two branches of physics that are somewhat far apart. One being general relativity, which explains why things move in space and the way they do, and quantum physics, which explains the building blocks of matter. So just how will this theory be proven? This is where the James Webb Space Telescope comes in. The jwst has been in development since 1996 and was expected to launch in 2007, but it's seen so many delays due to scheduling crisis, redesigns, increased cost, name controversies, and of course the pandemic, which almost scrapped the project altogether. The telescope was finally launched into space on the 25th of December 2021 from a European space agency in Kourou, French Guiana, with the estimated cost of construction being approximately $10 billion. The telescope is said to be the most sophisticated technology we've ever sent into space. It consists of 18 hexagonal mirror segments made out of gold-plated beryllium. These segments combine to form a massive mirror about 21 feet. It'll be able to detect really low frequencies through its infrared lens. The telescope is meant to be kept cool at all times so it can observe information undisturbed from other heat signatures. It has a 5-layered kite-shaped sun shield which protects it from the heat of celestial bodies. It is orbiting at about 1.5 million kilometers away from the Earth, which is the farthest we've ever sent a telescope. The objective or mission of this telescope is mainly to observe the early moments of the universe, going back as far as the Big Bang and observing the birth of planets and all the cosmic entities we've ever observed. Understand that space-time works differently, and with the right equipment you can actually look back in time in outer space, and that's just exactly what the jwst is helping us do. It will also help us know if Hawking was right and primordial black holes were indeed formed as the byproduct of the Big Bang. If this holds true, it will take us a step further into understanding dark matter, thereby uniting general relativity and quantum mechanics, proving Hawking's theory once and for all. Engineers have been absolutely nervous since the launch of the telescope because there are a number of factors that can jeopardize the telescope and cause it to fail, sending $10 billion down the drain. But so far, it's successfully reached its orbit and is expected to start transmitting information soon. The telescope is truly a boon in our understanding of astronomy and cosmology, and with the information we'll receive, we'll be one step closer to understanding just how we get to where we are, and that will help us know just where we're going to.